Hello, Math 200 students. Welcome to section 3.2. So 3.2 and 3.3 kind of run together. It's easy to get them mixed up. 3.2, conditional probability and the multiplication rule. This is about the probability that two events both occur. So what's the probability that this happens and this happens? All right. 3.3 is about the probability that one event occurs in different various ways, in 1, 2, or 3 or more ways. So one event in multiple ways versus this is 3.2 is multiple events. All right. So maybe that and 3.2 is going to be the multiplication rule to deal with multiple events happening. Section 3.3 is going to be the addition rule, which is one event happening in multiple different ways. Okay. We've already talked about a little bit about how to find the probability that two events occur in sequence. Before you can find this probability, however, you must know how to find conditional probabilities. So in the previous section, we talked about like flipping a coin and rolling a die. All right. But sometimes those events depend on each other. Flipping a coin and rolling a die do not, but sometimes different events do. A conditional probability is the probability of an event occurring given that another event has already occurred. The conditional probability of event B occurring given that event A has already occurred is denoted by P with the parentheses and then B with a vertical line and then A. That's the probability of event B happening given that event A has already happened. The way that we say this for short is the probability of B given A. The probability of B given A. All right. Example 1. Two cards are selected in sequence from a standard deck of 52 playing cards. Find the probability that the second card is a queen given that the first card is a king. Okay. If you don't know much about playing cards, that's going to be a hindrance to you in this unit. I'm going to try to show you something that might help. Okay, here is basically the entire deck of cards laid out in order. Okay, these are called ranks. All of these are called ranks. So you have ranks. The ranks are 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, Ace. Those are all ranks. These are called suits. So there are 13 ranks and 4 suits. The suits are hearts, diamonds, clubs, and spades. Hearts, diamonds, clubs, and spades. Hearts and diamonds are both red color. Clubs and spades are both black color. Okay, so the 13 ranks and the 4 suits make up how many cards total? 4 times 13, that's 52 total cards. Okay? So if you aren't familiar with a deck of cards, hadn't played much cards in your life, you might want to take a picture of this or draw this out for yourself to become familiar with these ranks and suits. Okay? So now back to our problem. 2 cards are selected and the probability that the second card is a queen given that the first card is a king. All right, let's look back at our deck of cards and see if we can figure that out. So we got 2 cards. First card, second card. We want the probability of a queen given, so the second card is a queen, given that the first card is a king. Okay, so what's the probability that we pick the first card as a king? The probability that we pick the first card as a king would be how how many ways can I pick a king? Okay, look at, here they are. Here are the kings. How many different ways could I get a king? 4. 4 out of how many total ways could I draw a card at all? 52. So 4 out of 52. Or you could say 1 out of 13. You could say it that way too. You could say, well, you could have said to yourself, well, 4 out of 52 reduces to 1 out of 13. But you could have also said, well, there's 13 different ranks, and kings is one of those ranks. So probably that I get a king is 1 out of 13. Or you could say 4 out of 52, which is the same thing. Now, what's the probability that I draw a queen given that I've already picked a king on the first card and I didn't put it back? Well, the probability that I pick a queen is going to be, how many queens are there? There are 4 queens. So 4 out of what, though? I've already gotten one of these kings. I don't know which king I got, but I got one of these kings already. So how many cards are now left in the deck? There's only 51 cards now. So 4 out of 51 would be the probability of getting a queen, given that I already got a king on the first card. So now I multiply these two probabilities together to get the total answer. All right, so looking back at this problem, I'm actually realizing here that I got a little ahead of myself. I got ahead to the next few examples, but it doesn't actually ask me what's the probability that I get a king and then a queen. It's just asking me the second part. Find the probability that the second card is a queen, given that the first card is a king. So looking back, the only thing that they're asking me to find is this part right here. Okay, the 4 out of 51. That's what they're asking me. What's the probability that I get that the second card is a queen, given that the first card is a king? What I was doing earlier was I was finding the probability that both of those things happen. But it's just wanting to know what's the probability that the second thing happens, given that the first thing happens. So the answer to that is just 4 out of 51. All right, let's read the explanation in the book. Maybe it'll help you, keep you from being confused by what I said earlier. Because the first card is a king and is not replaced, the remaining deck has 51 cards. So 4 of those cards are now queens, so 4 out of 51 is the answer. Okay. If you do that as a decimal, it's 0.078 or 7.8%. All right, number 2. The table at the left shows the results of a study in which researchers examined the child's IQ and the presence of a specific gene in the child. Find the probability that a child has a high IQ given that the child has the gene. All right, so we're looking at this whole table here. Okay. And it says, find the probability that the child has a high IQ given that the child has the gene. So we're not looking at this whole table actually, because we already know that the child has the gene. The gene is present. So we're really only concerned about this column. All right. So what's the probability, given that we're only looking at the children who have the gene present, what's the probability that the child has a high IQ given that he has the gene? So probability that they have a high IQ would be 33 out of the total that have the gene 72. 33 out of 72. Okay, 0.458. I want to do this try it yourself one. Why don't you go ahead and do the try it yourself and then we'll do it together. The try it yourself down here. All right, go ahead and try it. Okay, referring to that study in the second part of example 1, so referring to this gene and IQ thing, find the probability that 1, a child does not have the gene. Okay, so the probability that the child does not have the gene, so that means we're looking, it didn't say given anything. It didn't say given that anything. So we're looking at the whole table. What's the probability that the child does not have the gene? All right, the probability that the child does not have the gene is the total number of children that don't have the gene, which would be this. 30 children don't have the gene. What's the total number of children? 102. So the answer would be 30 out of 102. Okay. And then part 2, it says a child does not have the gene given that the child has a normal IQ. Okay. So let's think about that. What are we given? Given that the child has a normal IQ. We're given that the child has here's the normal IQ right here, right? So we're given that. So we're only looking at that information because it says given that that is the case. So given that the child has a normal IQ, what is the probability that the child does not have the gene? Does not have the gene would be this, 11 out of the total that out of the total that have a normal IQ. So the probability that the child does not have the gene present, given that they have a normal IQ, would be 11 out of 50. All right, so now we're going to talk about the definition of independent or dependent events. In some experiments, one event does not affect the probability of another. For instance, when you roll a die and toss a coin, the outcome of the roll of the die does not affect the probability of the coin landing heads up. These two events are independent. They don't affect one another. They're independent. The question of the independence of two or more events is important to researchers in fields such as marketing, medicine, and psychology. You can use conditional probabilities to determine whether events are independent. So here's our definitions. Two events are independent when the occurrence of one event does not affect the probability of the occurrence of the other event. Two events A and B are independent when the probability of B given A simply equals just the probability of B. All right? Or when the probability of A given B simply equals just the probability of A. So let me give an example of that. So what's the probability that you roll a 3 given that you just flipped and got heads? Well, it's still 3 out of 6. Because the flipping and getting heads doesn't affect the probability that you roll a 3. So the probability of 3 given heads equals the probability of 3 in general. So A did not affect B. Same way if we go the other way. What's the probability of getting heads given that you roll a 3? Well, that's just 1 out of 2. The rolling 3 doesn't affect whether you will get heads or tails. So probability of heads given 3 is just simply equal to the probability of heads in general. All right, events that are not independent are dependent. So when this is not true, when the probability of B given A is not equal to the general probability of B, then those events are dependent, not independent, because somehow there's an effect going on between them. All right, to determine whether A and B are independent, first calculate the probability of B, then the probability of, first calculate the probability of B, then calculate the probability of B given A. And if they're not equal, then they're dependent. If they are equal, they're independent. All right, let's see if we can classify events as independent or dependent. Determine whether the events are independent or dependent. Select the king from a standard deck of 52 playing cards, not replacing it, then select the queen from the deck. All right, so here we go. What's the probability of selecting a queen in general? 4 out of 52, right? What's the probability of selecting a queen if you already selected a king first? Then it's 4 out of 51. These two things are not equal. Therefore, we are going to say that they're what? They're dependent. All right? Tossing a coin and getting a head, then rolling a 6-sided die and obtaining a 6. So, what's the probability of getting a 6? 1 out of 6. What's the probability of getting a 6 given that you already tossed a coin and got heads? Well, it's still 1 out of 6. These are equal. These two events are independent because they don't affect each other at all. All right, number 3, driving over 85 miles per hour and getting in a car accident. Okay, this is more of an intuition thing, right? Because we don't have any data to base this off of in front of us. But what do you think the answer they're going for? Does the speed that you travel affect your probability of getting in a wreck? I think intuitively we think the answer is yes, and there would probably be data somewhere in a study to back that up. So given that this is affected by this, how do we classify those events? They're dependent. All right. Okay, the multiplication rule. This is actually, I already gave an example of this when I got ahead of myself earlier. To find the probability of two events occurring in sequence, you can use the multiplication rule. The probability that two events, A and B, will occur in sequence is the probability of A and B equals the probability of A times the probability of B given A. If events A and B are independent, then the rule can be simplified to simply this. The probability of A and B occurring both is equal to the probability of A times the probability of B. Why? Because if they're independent, then the probability of B and the probability of B given A are the same thing, because A doesn't affect B at all. This simplified rule can be extended to any number of independent events. So, okay, let's do example 3. Two cards are selected without replacing the first card from a standard deck of 52 playing cards. Find the probability of selecting a king and then selecting a queen. This is exactly what I did earlier. Probability of selecting a king and then a queen. If you don't replace it, well, first you get a king, that's 4 out of 52, and then you get a queen, that's 4 out of 51, given that you've already taken out a king and haven't replaced it. So the probability of both of those events occurring would be multiplying those two probabilities together, which would be 16 out of 26, 52. That's 4 times 4 and 52 times 51. And you can see down here that is equal to 0.006. All right, number 2, a coin is tossed and a die is rolled. Find the probability of tossing a head and then rolling a 6. What's the probability of getting a head, getting a heads whenever you toss a coin? 1 out of 2. What's the probability of rolling a 6, given that you've already flipped and got a heads? Well, it's just 1 out of 6, which would have been that regardless. 1 out of 6. So this is an example of when the events are independent. All right, so that's going to be 1 out of 12, right? So the answer is 1 out of 12 there. All right, go ahead and do the try it yourself for number 3 here. Go ahead and do those two on your own, and we'll do them together. All right. So the probability that a salmon swims successfully through a dam is 0.85. Find the probability that 2 salmon swim successfully through the dam. All right, I think I'm going to be safe in making the assumption that the first salmon swimming through the dam successfully does not affect the other, whether or not the second salmon can successfully swim through the dam. All right, so what's the probability that the first salmon swims through the dam? 0.85. What's the probability that the second salmon swims through the dam? Again, 0.85. I think these are independent events. So all I have to do is multiply those two things together to get there. So it is 0.7225. All right. Second one, 2 cards are selected from a standard deck of 52 playing cards without replacement. Make sure you heed when it says without replacement. If it said with replacement, it would be different. I'll show you what I mean. Find the probability that they are both hearts. All right, so what's the probability that the first one we do is a heart? How many hearts are in the deck? There are 13 hearts in the deck, so 13 out of 52. But we didn't replace that first heart, so now what's the probability that we get a heart on the second draw, the second card? Well, there's only 12 left in the deck because we've already got one of them out of there. How many cards are left in the deck? Well, since we've already got a card out of the deck, so it's only 51 cards. So the probability that we get a heart and then another heart is going to be 13 out of 52 times 12 out of 51, which would be, let's see, 13 times 12 is 156 divided by 52 times 51, 2652. Now, if it had said with replacement, if it had said with replacement instead of without, then it would have been just 13 out of 52. But we replaced it, so the probability for the second one is again 13 out of 52. All right, and that would have given us 169 out of out of 2704. Okay. All right, for anterior cruciate ligament ACL surgery, the probability that the surgery is successful is 0.95. Find the probability that 3 ACL surgeries are successful. I think we can assume here, since they didn't tell us anything about them affecting one another, that those are independent events. Like one successful ACL surgery does not affect another ACL surgery. So we got 3 events, 3 things happening. So probability that we have a success on the first one is 0.95. The probability we have success on the second one is 0.95. Probability we have success on the third one is 0.95. So we multiply all 3 of those together to get the probability of having success in all 3. So the probability of having 3 successful surgeries is 0.857. Find the probability that none of the 3 ACL surgeries are successful. Okay? Still got 3 events, and none of them are successful. That means the first one is not successful, the second one is not successful, and the third one is not successful. Well, what's the probability that the first one is not successful? This is where you're going to use the concept of a complement of an event. If the probability that it is successful is 0.95, then the probability that it's not successful is 1 minus that, 1 minus 0.95 or 0.05. Probability that it fails is 1 minus the probability that it succeeds. All right, so what's the probability that the second one is a failure? 0.05 also. What's the probability that the third one is a failure? 0.05 also. So the probability that none of the 3 are successful is multiplying the 0.05s together, which is 0.000125. Pretty low, really low. Number 3, find the probability that at least one of the 3 ACL surgeries is successful. All right, here's a difficult way you could do that, and then I'll show you an easy way. The difficult way is to say, well, the probability that the first one is successful is 0.95, and then the next 2 are unsuccessful is 0.05 and 0.05. The probability that the second one is successful, but the other 2 aren't, is 0.05, 0.95, 0.05. But we got to find the probability that at least one is successful. So we'd have to add this one and do another one where the third was successful, and then we have to do one where 2 of them are, the first 2 are successful, or the first one and the last one are successful, or the last 2 are successful. And then the probability that they're all 3 successful, we have to add all that stuff together. That's a really difficult way to do it. The much easier way to do it is using the concept of the complement of an event, which is really, really handy oftentimes. All right, so the way that we can do that very easily is we can say the probability that at least one is successful. Why is this eraser not working? Please work. Okay. Is the complement. It means any of them can be successful. And that is the complement to none of them being successful. The probability that any of them are successful is the complement to the probability that none of them whatsoever are successful. So, the answer to number 3 is 1 minus the answer to number 2. So it's 1 minus 0.000125, which is 0.999875. All right, another example. About 16,500 U.S. medical school seniors applied to residency programs in 2012. 95% of the seniors were matched with the residency positions. Of those, 81.6% were matched with one of their top 3 choices. Medical students rank the residency programs in order of preference, and program directors in the U.S. rank the students. The term match refers to the process whereby a student's preference list and a program director's preference list overlap, resulting in the placement of the student in a residency position. Find the probability that a randomly selected senior was matched with a residency position and it was one of the senior's top 3 choices. Okay, so we're talking about he was matched with the residency position. So that's first of all. What's the probability that he was matched with a residency position at all? 95% of the seniors were matched with residency positions. So 0.95. Okay. Next. And it was a top 3 choice. Okay. It says of those, 81.6% were matched with one of their top 3 choices. So 0.816. So multiply those two together to get the answer. And the answer is 0.7752. All right, number 2. Find the probability that a randomly selected senior who was matched with the residency position did not get matched with one of their top 3 choices. Find the probability that a randomly selected senior who was matched with a residency position did not get matched with one of their top 3 choices. So we're saying given that they were matched with a position, that they were not one of the top 3 choices. So this is simply the complement of that. So because we're already given that they're matched. So we're already given this part. So we're not worried about that. That's already happened. It's given that that's already done. It says of those, these were matched. So what's the probability that they weren't matched, given that they were part of that 95% that were matched with that they weren't matched with a top 3 choice. So it's going to be 1 minus 0.816, which is going to be 1 minus 0.816 is 0.184. All right. Would it be unusual for a randomly selected senior to be matched with a residency position and that it was one of their top 3 choices? So this is just going back to number 1. We already found that probability in number 1 right here. So would that be unusual? Would that be unusual? No, it wouldn't, because it's like a 78% chance of it happening. So it definitely would not be unusual. It'd have to be less than 5%, less than 0.05 to be considered unusual. So the answer to that question is no, it would not. All right, so that finishes up section 3.2. I think some of that's probably a little confusing, but hopefully you will get the hang of it. Good luck on that assignment. I'll see you again in 3.3.